waiting for a video. There we are. Hey everybody, hope everyone's doing well today. So in our schedule here we are in week 4, and today we're going to talk about, I'm going to talk a little bit about templates and a little bit of example from the material from video module 3. I meant to leave a note on Canvas saying that you need to do video module 3 before class, but I forgot. Sorry about that. So we're going to pick up there. And then this week's video module talks about task sequences, and so it's going to pick up from material that we do in class. So I think I have these in sync now, where the video module is going to follow up from what we do in class. Let's see what else here. So I mentioned on the first day of class that some weeks we'll go over, but I will make it up to you. This might be a makeup week because we have a basketball game at 6. And at least one of us in this room wants to see the basketball game. So luckily, the one of us in the room who wants to see the game at least is the one of us who gets to decide when we're done. Okay, so let's pick up with the material for today. I've got a couple of questions. These are pretty kind of tie into what we're going to talk about today. The first one asks about auto-create, in particular the xloc and zloc from the first video, and are they necessary? And so I brought in the model, or a version of the model that I did in that module. This is the model that we did in video module 3, or one version of it. And the question kind of revolved around this auto-create. So we have this table of resources, and it uses auto-create instance, and there's a connection to the object type O type, and then there's connection between xloc and zloc, and of course that defines the location for those object instances. And so there's that two-way connection. So if we go back to, say, S1 and move it, then we see that connection is two-way, and so it updates the data in the table. So the question that I got was, well, do we have to do that? Do we have to have xloc and zloc? And the answer is we do not. We don't have to have those. Second half of the question was that a particular student got an error when they deleted them. Okay, and so the reason that if you went to this one and deleted these two, that you would get an error is because we have a connection right here. So in the auto-create column, under resources, you have a connection to xloc and zloc right there. And that's what causes an error when you do that. But if you don't have that connection, so if I went and said, let's create a new table. I'll just leave it table 1. We'll just have an object reference property. And I'm going to say auto-create. And instead of using O type, so in the previous one, I have a separate column for the type, but you don't have to do that either. I mean, I could specify the type. So if I wanted to have a separate column for all, let's say, the server objects, a separate table, I could do that. So I could just go in here and say, make this server. And then we could do, S111, because I have S1 already. S222, S222. And then if you go back to the facility, there they are. And so they get created. And so there's no requirement to have the location. There's no requirement to have the type. We just use those because it makes it more convenient. And again, the reason you have an error in this one, if you try to delete X and Z, is because they're tied to that auto-create. If you deleted those references from the auto-create column, then it would work equally well. That's question 1. Question 2 has to do with the part table, and in the model that we did in the video module and that we're going to pick up with today in class also, I used a string state to define parts rather than an entity type. And the question is, why do you do that? And can you not define an entity as a property? And so the answer is yes, I can define the entity as a property. I chose to do in this one, let's see, go right here, to define the parts using a string state because I didn't want to have separate entities for each part type. Right? If I define this as an entity type, everything works the exact same. Right? I can still define that as a key column. I can still use it as a foreign key. But what it requires is that I have unique entity instances for each part type. Right? And so if I made that an entity column, I think we did that in one of the earlier models maybe. I could do it, and I could actually use auto-create. So I could auto-create the entity instances, and each different part type would have a different entity instance. For this particular model, I just didn't want that. What I wanted to do instead was to have an order instance. So if you go back to my model, we have this single entity instance called order. And so every order that gets created is a member of that order population, regardless of what part type comprises the order. Okay? Again, that's a choice I made. Had I wanted to have a different entity instance for each one, I could easily do that. Just change that column type from string state to entity state. I could still have auto-create. I don't have to have auto-create. And what's going to happen is if I have auto-create, it's going to create an entity instance for each one. And then I would have a separate population for each one of those part types in this case. Yeah.
But in this case, if we create like every part of that entity, if we want to get the completion time for an order, then we need to do something extra to link that part with, I don't know.
Well, so if you did that, so in this case, again, I have orders right here, and so everything is an order. And so when I end up running, I have a population. Where's my orders here? I have a population of order. And so I can get population statistics by order. If I want population statistics by part type, I have to manually get that here. I would have to go in and say, I want to track this. On the other hand, if I did individual instances and I wanted population information about everything, I would have to go in and manually track that. So, there are two different ways. It's not a right or wrong. It's just what you want the design to be. Okay? And lastly, had to do with templates, which is, again, good because we're going to use our template today. And it says, when we make this available, it's only available for our future use and not for others. Right? So when you copy this into the Simio directory on your computer and do new from template, then it's only available to you. It's not available to anyone else. So the question then, is there a place to share it? And the answer is yes. There is some sharing, not as much as you might think. It's pretty complicated to share because you have to document and all that. But if you, as I talked about in the very beginning of the class, join Simio Insiders and have access to the Simio forums, there is a specific forum here for shared items. And in that shared items, you have not only templates, but also libraries, path decorators, texture symbols, that kind of stuff too. And so anybody who wants to share can share here. And so it's not controlled by Simio, the company. It's monitored, but not controlled. And so again, the level of detail of what you'll see is highly variable. From, hey, here's a template which doesn't really tell you anything, doesn't have much documentation or anything, to, hey, here's a library that's completely documented. Right? And so you see a whole bunch of stuff there. And that's a place where you can look and you can share stuff if you so desire. And so that's the 3 questions I got this week. Does anybody have any other questions for me before I pick up and cover material starting today? Okay. So last time we started talking about Simio, simulation-based scheduling and Simio RPS, and went through this notion that simulation-based scheduling is a general technique, and the general technique basically says I'm going to use an event calendar, and I'm going to systematically create the event calendar using this notion or using this concept of discrete event simulation. And I'm going to go back once I have the event calendar completed and extract scheduling information from that. And Simio RPS is a commercial product that incorporates several features that simplify this, and we saw all of these things in class last time. And so what I want to do today is pick up there and do a really quick example. And I will tell you, I thought about doing this example as a video, as one of the videos in this week's video module. And I decided I would give it a try in class. There's a little bit of interaction that I have to do on the computer, so we'll see in the end if it was a good decision to do it here versus doing it in the video module. So what we're going to do is we're going to start with a slightly modified version of the template that I built in VMO3. So I have a template, it's called Job Shop Template. That's on my computer, and I'm going to start from there. And before anyone asks, no, I'm not going to share this with you because I want you to be able to build it yourself. That's part of what we did in Video Module 3. However, if you run into problems and you can't reconcile the problems with what you see me do with what you're trying to do, I'm happy to help and all that. I'm just not going to send you the template because I want you to build it instead. And we're going to build a 3-stage flexible flow line model. And then we use this model, as I said, this week's video module 4 follows on from here because we pick up with the model that I'm just about to build. We pick up with that in video module 4 and do some more technical stuff. And so to refresh your memory, we have this template. That's not my template here. There it is. This is the template, or again, it's a slightly modified version cleaned up actually, of the one that I did in the video module. And as we've discussed based on the question, when I build this template, I can then store the template in a particular directory in the Simio installation tree, and then I can do new from template, which I'm just about to do here in just a second. So that's, I'm going to use this template. And the template that we developed has a couple of core components. The first one is a specific data table structure. And there's a specific, an ER diagram for the specific data table structure. And you can see that I have 4 tables. A set of resources, which we just saw, uses auto create. I guess I forgot the, oh no, the O type's there. The resources table. Then we have a part table and a sequence table. The sequence table defines the processing sequence for each part. And then we have a set of orders, and the orders have an arrival date, part which is a foreign key, quantity, due date, release date, completion time, and so on. Okay, so we have this specific table structure, and there are fixed relationships in that table structure that we use. We use that relationship so that once we set a table row reference, when we use the arrival table, we have access to all of the information over all of the tables through that relationship structure. So the other thing that the template includes is a set of modules, custom objects, that use this data table structure. So we had a source object, which is set to have use the arrival table, and it also sets, what does it do? It uses the arrival table, does one other thing, I forgot what it was though.
Release.
The release, yes. We have a server. The server then, a couple things. The server implements the processing time based on the order quantity times the part processing time. It also uses the by sequence routing mechanism, which the source did also. So the output node from the source object uses the routing by sequence, which is not the default behavior of a source. And then finally, we have the sync, which records that completion time. So when an order comes through the sync, it automatically records that completion time. And so what I'm going to do today is I'm going to use that structure. And so I have an Excel table here, an Excel workbook, that I'm going to use to build this flexible flow line model, and then we're going to talk about that. Okay? So let's do that. Pretty straightforward process. I have a Simio model here somewhere, my Simio project. And so as I said, when we want to use a template, we go new from template, and then there is the template that I just did. And when we do this, this is really a shortcut. So what this does is a shortcut, and it's really not that much different than if I had just opened that file, template file, and saved it under a different name. Okay, the only thing it does different from that is that it sets a couple of bits in the Simio model so that Simio thinks the model hasn't been saved before. So when you try to exit, it says, do you want to save this? And it doesn't have the name. But everything else is the same as if you just do the save as. Okay? So there it is, and there's my order. And as I said, we have our table structure here. And so what I'm going to do, as I said, is I have an Excel spreadsheet with all of the data, and I'm just going to copy all of that data and paste it in. Okay, so pretty straightforward. Here's my resources. So I'm just going to copy. And remember, when we paste, we have to select the cell, hit escape, and then hit Control V. So what that's going to do, because we have auto create, I already have my location set up, it then creates all of the instances that I'm going to use in my model. Okay, and as I said, when you look at the order, we have the order table set up here. I have the by sequence set up here. So all of that is due to the use of the custom object. Okay, so one other thing to note here is when I look at these, when I look, say, at this one, the property values are not bold because these are the default property values for my custom objects. You know, if I had an arrival table for a normal source, so if I drag a normal source out here and say, hey, I want to make this by arrival table, so I just go back and say arrival table and use the same table, for example, everything is bold, right? Because I've changed something from the default, and that use of bold is really helpful because it can tell you what things are at their default property values and which ones have been changed. But we're not going to change those for this one. Okay, so first step, create that. Second step, I'm going to create my parts. So go back to my spreadsheet here, grab my 3 parts, copy those guys, go back into parts, paste. And as with the previous one, these are string states, so I'm not using part entities here. I'm using the order entity exactly as I did before. Also note here that I have an output column called total P time, total processing time. And so in my Excel, I didn't have that property. I didn't have that column, right? So I just pasted the values in from the columns that I have. And so you don't have to have all the columns, right? And if you paste them in, it will just paste those in. Of course, this one is an output, is a state column. So it's going to get written by when we execute the model. Go back and choose the sequences. So go back and choose sequences. There they are. Copy those. Control V. So there they are. And as I said, we use this relationship structure. So I did nothing other than paste the values in, but it inherited that relationship structure so that I can look in the detail view and then see for each one of the parts what its sequence is. And so you can see that part A goes S1, S2, S3. Part B goes S1, S2, S3 also. Part C goes S1, S3. So a flexible flow shop is one where everything flows in one direction, but you can skip stages. Like in this one, part C doesn't go to stage 2, and the processing times can be different. Right? So that's the definition of what a flexible flow shop is. And then finally, I'm going to go and paste the orders in. So go look at my order table here. And as with the parts, I have a whole lot more columns than I actually have here, right? That I have in my Excel. So I have my arrival date time, my order ID, part, quantity, due date, no release date, no completion date, no total processing time, and then of course the delivery is a target, so you don't read that value in. So just grab all these guys and paste them in. Okay, and so now I have this and I can go run my model. Right, so if I run my model, there it goes. I can run it to the end, go look at my results, and go look at the results we're interested in from a scheduling standpoint, the Gantt charts and all of that. Okay, so again, we built this model without doing any editing. We just pasted the values in, right? And because we had the template set up that uses the table structure and the custom objects, we didn't have to do any coding. So the whole idea of using custom objects and templates is so that you can reduce the amount, and so that you can hopefully move towards having a completely data-generated model. Okay, so when we do real models, you will almost never have one that's completely data-generated. You're almost always going to have to go in and do some editing. These are really, really simple models, but it gives you a really nice starting point. Okay. Let me reset this here, talk about that. And so one more comment that I want to make here before we move on is to talk about the fact that I pasted these values in from Excel rather than binding them. So in the video, we talked about binding the tables, and so that you can read the values in. And I think we went through a couple exercises where I modified them in Excel and then reread them in and all of that. Okay, and so pasting them in and binding them are two different things. Sometimes it's easier to paste them in, sometimes it's easier to bind them. But a typical use case for a scheduling type model, you would want to bind the order table, because once you have the model built, the models like this that you build, you use to do scheduling. So think about doing a weekly schedule. I'm going to bind my orders table. Once I have the model built, I'm going to bind my orders table to something that comes from a planning system. whether it's a CSV file that the planning system gives me, whether it's a direct table query so that I go into the planning table and grab everything, right? And then the resources table, you can bind or not bind, but you don't really regenerate the model that much. You can, but it's just not a general thing that you redo. The parts and sequence table, again, a choice that you have depending on the infrastructure, your information infrastructure. So if you have, say, a bill of materials table in your planning system, you can also bind this to that so that every time new parts are created, you can automatically import those into your model. Yes, sir.
So I was wondering how binding works. Does it work based on a relative path or absolute path of the file? So, for example, if we move the Simio model out of the folder that it was originally created in, or we move the CSV file to a different directory?
You can set the bindings to either be an absolute path or a relative path. If you're going to move things around, you need the plan, right? So if you read them directly, so if you don't set a path, it's going to look for them in the directory where the model exists. But you can set absolute path. And of course, if you read from a database, you just have to have the database connection set up correctly, and it will connect from wherever you happen to be from if you have a path, a network path to get to that database. Anything else? Okay, so we built the model, and again, we haven't done any real editing at all. Okay, and so when we go in and look, let's go in and look at our plan here, and note that when I ran before, I didn't run in planning mode. So we have these three different modes. We have interactive mode, which we did run, planning mode, and we have experiment mode. So when I want to run in planning mode, I can create the plan there. Okay, and so if you look at what's going on here, if I just let's open this up and look at my constraints. What we can see from here is, again, we have a flexible flow line, so everything comes in at S1. S1, S2, S3, and some of them skip S2. Okay? So what looks like it's happening is we have a batch of things that arrive at time 0, and then we have a batch of things that arrive sometime later, right? And so you can see those constrained entities. So go back to our data table and look at that. Back to our data table, you can see that all these guys arrive at the start time of the model, which happens to be the 7th of February at 7 a.m., and then everything else arrives the next day. So today, this morning, February 8th, at 7 a.m. So that's what you see in that when you look at this plan. Okay? We also have in the template, you have the entity workflow. And so because we have that target set, we have the on-time performance indicators here. And so you look, this order is clearly late, this order is clearly late, and so on. So you get that information directly. We have a couple of dashboards that are built into the template. I have the two dashboards that I did in the video module 3. One is the dispatch list, and the second one is the make span. Okay, so we read the values in, build the model, execute the model, and then we have all of this general planning information. Okay? Any questions for me? Okay, so now we're going to do a little bit more detail about, how things work here. So to do that, I'm going to go back and stop. I'm going to turn on model trace. We're going to look at some details here. See how I want to do it. Okay, so I have trace on, and the first thing I'm going to do, I'm going to go through and look at how this model executes. So we've talked about sort of in a conceptual level of using discrete event simulation in the context of a schedule generator. Okay, so now I want to do a little bit more of a dive into some of those details. So what I'm going to do is I'm going to start the model in step mode. And when I run in step mode, what that does is it runs the model sort of one event at a time. It's not exactly one event at a time, but you can think of it that way. Okay, so when I did step, what it does is it executes the on-run initialize process. And if you remember, the on-run initialize process, if you remember from the video, what it does is it goes in and calculates those total P time values, right? Since a part has multiple station visits that are defined by the sequence, if I want to know what the processing time for a part is, I have to add that up. And so that we did that with this onRunInitialize process, and go look at my part table, and those values were computed. If you remember, when we read the values in, we didn't read them in from the table because we just computed them in the onRunInitialize. And same thing for the order. So the order, I want to be able to compute the total processing time, the total raw processing time for the orders, which is a combination of the part processing time times however many of those parts that I have. Okay, so that first thing it computes that. And if we look, we can see that happening right here in our trace, onRunInitialize. Okay? And so one thing I wanted to point out here as we go is sort of the usefulness of using trace and using model documentation. And so you can see in my onRunInitialize, I have names for all of these steps. So we don't just see search 1, search 2, search 3, assign 1, assign 2. Right? They have names for them, which makes the process infinitely readable, hopefully. Hopefully you can look at that and say, the first thing I do is search the part table. And then for each part, I search the sequence table. And then for each sequence element, I accumulate the total processing time. And then if you move to the right, you say, then I search the order table. And for each order, I accumulate the total order time. And so by just reading those comments or reading the step names, you should be able to get a good idea of what's going on. The other common thing is by using step colors. So I can go into my steps and say, I'm really interested in this step, my 2 assigned steps. So let's give these colors. Let's give the one of them orange, and then we'll give one, I don't know, green. Green. Here we go. And so now when I execute the step, if I go back to my facility and go back in and step, you can see that the corresponding entries in the trace window have those same colors. And so it makes it really easy to see what's going on. Okay, so let me just stop for a second and say the models that we've done so far have been very, very easy. They're going to get successively more difficult as we go on. You will spend time in trace. You will absolutely spend time in trace. Okay, so make sure that you understand how to use it and you understand what tools are available. And these are the 2 of the best tools is naming the things appropriately so that you can remember what you did the day before or the week before or whatever. And using step colors so that you can see actually what's going on. Okay, so that was an aside. That's really not the scheduling part. I say the same thing when I do general simulation models. The same thing applies. That's not just for scheduling models. Okay, so anyway, we've stepped. I stepped forward, and so all we did is run into the onRunInitialize. And so I'm going to continue to step here. So I'm going to step here. So the first thing, I'm going to zoom in here because I want to see what's going on here. As I said, conveniently, we have this flexible flow shop, so everything arrives at the source and everything immediately goes to 1. So I can zoom in and I'm not going to miss anything. Okay, and so I execute one step. And so this order 1 goes to S1. And let me just do a couple more here. So there's order 2. There's order 3. There's order 4. There's order 5. And there's order 6. Zoom in enough, you can see that. So 1, 2, 3, 4, 5, 6. Okay, so it just read those in from the table, because our first 6 entities arrived at time 0, which is this time. Right, so this is February 7th, 7 a.m. Or you can also think of it as 0 hours in constant time, or in raw base simulation time units. Okay. Now, when we look at this, the first question you should ask, or you should wonder, why doesn't S1 immediately go to server 1? Right? So what should happen, right? Remember how we implement the server logic. Well, server logic basically says an entity comes up, and if there's server capacity, it gets it. Otherwise, it gets in the queue. Okay, but that didn't happen here. Right? Because 1 got there, there was nothing in the queue, so there's capacity available. But it didn't get there, right? It didn't immediately start service. It just sat in the queue. Okay? Now, when we talked about dispatching last time, I made a point of saying that when you use a dispatching-based model, it's almost impossible to induce forced idle time. Okay? So you might be wondering, aren't we inducing forced idle time here by not letting 1 progress into service, waiting for all of the others to arrive? Okay, but we're not, because everything is still happening at time 0. right? We're still at time 0 in our simulation model. We haven't progressed at all. That's because we had all 6 of the parts arrive at time 0. And because we have the speed for our order entity instance to be infinity. So what's going to happen is the part's going to, or the entity's going to arrive. It's going to say, okay, I'm going to move to this new node. Let me calculate the time it's going to take. Well, it's going to take 0 time. So it's going to create an arrival event at time 0. And it moves. Okay? I have a second arrival. It arrives at time 0 and so on. So what we see is that we have a whole bunch of events and they're all happening. They're all scheduled to happen at time 0. Okay, they're all scheduled to happen at time 0. But they can't all happen simultaneously. Right? A hallmark of discrete event simulation is that you have to execute the steps sequentially. Okay, you have to execute the steps sequentially, even though they're happening in 0 simulation time. Okay, and so this particular situation here, where I have order 1, because order 1 didn't immediately start service, that's a design decision from the model. Right? That's a design decision because you can think about having an event calendar, and in any event calendar, I can have an arbitrary number of events that happen at a given time. And as I said, you have to execute those sequentially. So someone has to choose the order that I'm going to execute those. Okay, so for example, let's say suppose that I went ahead and started S1 processing. Started order 1 processing. Well, that's going to preclude starting the order 2 processing at time 0. Right? So the sequence that I choose, even though I have all of these events that are happening at the exact same simulation time, I have to do them sequentially, and the sequence that I choose has an impact. It has effect on how the simulation works. Yes, sir?
So is this prioritization of the things that happen concurrently, like the software has to pick one to run at a given time, right? So sequential. Is that choice affected by the optimization of the code, by, like, how is this?
Yeah, I'm going to talk about that very thing right now. Okay, I'm going to talk about that very thing in just 2 seconds. I just want to make it clear what's going on. Again, this happens all the time in discrete event simulation. You have an event calendar, and remember how the event calendar, the discrete event simulation works. I have an event calendar, I start putting stuff on the event calendar, and then I jump to the time that the next event happens, and I do the thing. And when I do the thing, when I execute the event, it causes new events to get placed on the event calendar, and so on. I just continue doing that. But as I said, a lot of times you have multiple events, so you have to choose a set of sequence for how you're going to do those. Some of those choices are made internally to the software, and some of those choices you, as the model developer, can make. Okay, so in this case, let me go back to my PowerPoint here. Here's what we did. What we just are implementing here is a dispatching, right? So what I have here is I have a ranking first in, first out. And so this idea of selecting from among the waiting tasks. Okay, so what I did is I want to have a model where I now have all of my 6 orders, and I can just choose how I do that. Choose the order that I process those. And so in Simio, we can, there are a couple ways to do that. One of them is with the ranking rule. And what the ranking rule does is it just sets the order in the queue. Okay, and you can just see here, we use first come, first serve. Just went down the order that we saw them in the arrival table, 1, 2, 3, 4, 5, 6. Okay, so now this question of, well, why doesn't 1 immediately go into service when it gets there? Okay, and so I printed or copied a couple of elements from Simio help. And I want to talk about something called late priority events. Okay, late priority events. So what this upper section is help from the server object. And what the lower section is the definition of something called math.epsilon. Okay, these are both pertinent to this situation. And if you look at what it says on the properties for server, these 2 properties are of interest. One is immediately try C's. An immediately try C's property can be set to true or false. And by default, it's set to false. Okay, and so what that's saying is I don't want you to immediately try to seize the resource when an entity arrives. Okay, and so instead of that, what it's going to do is it's going to induce a math epsilon delay. That's where math epsilon comes into play. represents the smallest value greater than 0. And here's the note that's really important to us. It says the standard basic node and standard transfer node objects do a delay math epsilon in order to guarantee the correct order of events. The delay step actually interprets math epsilon as a 0 delay, but forces the event to be put at the end of the current event list. So in essence, what it's doing is it's forcing a late priority event. Okay, so if I go back to my model, that's not what I wanted to do. If I go back to my model, I now have a late priority event that says allocate. Okay, and what's going to happen when I step now is everything has arrived. I now have everything in order. And so when I step, that next event, which is that late priority event, which means it happens at the end of the sequence of tasks that all happen at time 0, says, hey, allocate server capacity based on the ranking rule. Okay? Does that make sense? So this notion of late priority events is important. We're going to see that a lot. And we're going to see this notion of inducing, creating late priority events. Yeah?
Could you please go to the previous slide with the epsilon one more time?
Let's see here. Yeah.
So it use a delay of 0.0. So this is not perceived as a delay. But let's say we wanted to create 1 billion entities at the same time.
Okay.
So after 1 billion entities created, we have to induce 5 billion epsilons.
One more time?
So
I have 1 billion entities. I got that.
Gets created, so we induce 5 billion small epsilon math dot epsilon delays, right?
Okay, well, let's look at what delay math epsilon does for just a second. So you can think of it this way. Here's my event calendar. Event calendar. And let's just say here we are at time X. Doesn't matter what X is, okay? And so what happens? So let's pretend it's time X and I have an entity arrive. Okay, so I'm going to have an arrival event. Arrival. And so that arrival event, what's it going to do? Well, it's going to look at the table. It's going to get the entity. It's going to get all the information. Then it's going to say, hey, this entity, when I hit the output node, is going to say transfer, to S1. And then it's going to look at the part and say, hey, it's infinite time. So what's it going to do? It's going to schedule an arrival event also at time 0. So it's still time X, and we're going to schedule this is arrival table. This is arrival at node. It's going to schedule that. It's going to schedule it at the same time. Okay? And there might be other events right here. There might be other things that are getting processed here. Okay? Now, what you do when you say you induce a math epsilon delay, let's say for the sake of argument that I had, when it arrived at that node, I just put a step in that says delay math epsilon. What that's going to do is it's going to create that event at the very bottom here. So you're still at time X, but it's going to move it to the bottom. So if I had 1 billion entities, I'm going to have 1 billion whatever event gets created, but they're all going to be lined up here at the end of the step. So that what you're forcing everything to happen before I do those. And so in our example here, what I'm doing is I'm forcing all of the allocation requests to happen at the end of the time 0 step, so that I see that everything is in that queue.
So this math.epsilon effectively only affects the scheduling of events, right? Not actual simulation time, just the scheduling of events.
Well, when you insert a math epsilon delay, yeah, that's what it's doing. Okay? So if we go back, let's go back to our model. Real quick, I'm going to stop it here. Let's just say instead that I go look here at my server, because remember this is a job shop server, but it's subclass from server. So everything server has this at. So I can go in here to this other processing options and say, here's that guy right there. Here's the immediately try C's, and it's set to false. Suppose I set it to true. Okay, so now I'm going to say, okay, now immediately C's. Ignore that math epsilon delay. And so I go through the same process that we did before, and I step, and I step, and I step. And now when I step, it immediately has access to the server. So it's bypassed, or it's seized immediately. Okay? But what that does, in this particular example, is it's saying, okay, well, I still have all these other guys, and they're all trying to seize too. Since I have capacity 1, that none of them get the server. Right? So because that first one got it, just because arbitrarily it came first, even though they all get there at time 0, we couldn't use our dispatching logic to allocate server capacity. The server capacity was allocated before we got to use the dispatching logic. Okay? And so in the default implementation, which we saw here, I reset that to false. You see, we've had all of those things arrive. And so what happened behind the scenes is when order 1 arrived, it then scheduled an event to arrive at the node at the same time. It then went to that one, and then it said, okay, I'm at the node, but the node said, schedule an allocation for the server, but put it at the very end. And then the arrival table said, have another one arrive, and another one arrive, and another one arrive, and another one arrive, and then this evaluates when all of those things have happened. Yeah?
All this is just to deal with like the artifact that like, the computer can't look at more than one thing at once.
Correct. Yeah. So you have all of these things that happen sequentially in wall clock time, but you want them to happen instantaneously in
Like,
simulation
the
clock.
computer just has to go through the.
It has to go through them in sequence.
Yeah.
Yeah.
So it really doesn't make a difference in the time span. It's just more of like the order.
Well, the time span matters if you have events that don't all happen at once. Like, let's say, for example, that I didn't have infinite speed. When something arrives, it takes time to travel. Okay, so here it's of interest because we have a whole bunch of stuff that happens at the exact same simulation time. If that doesn't happen at the exact same simulation time, it's not as big of a deal.
But like what you did earlier with making the order 1 go ahead and go to S1, that doesn't change the time. It's still at 0.
No, it's still 0. So I should have shown that. It's a great question. So I'm not going to go back and redo it. But when I set that to true, to immediately try seize, it was still at time 0. And so it moved from the input station to the processing station, and it started the processing time clock, but it didn't move. So we still had all of the other arrivals, and it was still at time 0.
Technically, in like the terms of the event calendar, would the last thing at time 0 be moving order 001 to S1? Because would it still be at 0 when it hits S1?
Conceptually, yeah. It's not always the exact last thing, but it's always late. It's late relative to the other important things. Okay? All right, so we can do this. So let me just stop this and say, okay, well, let's go back and look and change our ranking rule. So we did first in, first out. Suppose I went in and said, let's do smallest value first, and let's use orders total p time. Right, because when we create an entity using the orders, it has that row reference. So I want to rank the orders by total processing time. So if I go back and look at my table, and I say, okay, that total processing time column over there near the end, what should happen? Well, it should be ranked, what is it, order 6, order 3, order 4, order 2, order 5, order 1. So if you just do smallest to largest of that total p time column. Okay, so in this case, I don't want order 1 to go first. Right? And so in order to be able to get that allocation, I have to let everything get there. And so I set that value, that smallest order p time, and now I go through and do the step. So 1's still there, because it still arrives first, because you still do these in sequence, the sequence that they appear in the order table. When order 2 gets there, now it moved. Right? So the ranking, I can't see it all here. And so what the ranking rule does is it basically inserts into the queue, or inserts into the input buffer in this case, in the right order based on that sequence. Okay, and so if I continue doing that, continue stepping, here we go. There's our sequence. I think that's the sequence we said, right? 6, 3, 4, 2, 5, 1. Okay, so now everything's arrived. Everything's in the queue. We're now at this last event in the event calendar at time 0. And so execute the event, and it then grabs order 6. Okay? Does that make sense? And so in this case, what we did was we used 2 different dispatching rules. I used first in, first out, and that ordered the queue 1, 2, 3, 4, the order that they actually arrived. In this case, since we used an arrival table, the order that they arrived from the arrival table. And in the second example, I used smallest value first for orders p time. So like a variant of shortest processing time. Okay? Does that make sense? Okay, so I'm going to go back. I'm going to look at dynamic dispatching rules. Okay, so let me go back here, stop the model, go back here, reset this guy. Still going to do first in, first out. Yeah?
So in the case study, what we need to do is like implementing all of different rules to compare how that impacts the main span and all the output.
One more time, I can't hear you.
In the case study, like we should implement different dispatching rules.
Yeah.
Yeah?
Yeah. Yep.
And then just analyze and compare the results.
Correct. That's what we're going to do. So right now, we're still in the technology stage of learning what dispatching is, how to implement dispatching rules. But the goal is to use dispatching rules to get the schedule that we want. Okay? All right, so I'm going to go back. I reset that. And the next thing I want to look at is dynamic dispatching rules. So you can look here in my properties. There's the ranking rule. There's this dynamic selection rule. And I'm going to use smallest value first. I'm essentially going to do a dynamic version of what we just did. And I'm going to do a dynamic version of SPT. Okay, and to do that, I have to use this candidate notation, which I will talk about in just a second. So bear with me here. So we're going to do candidate orders total P time. Okay, so when you do a dynamic dispatching rule, it's looking at everything in the queue. And so you have to use the candidate keyword to say, apply to this candidate, this candidate, this candidate. So it's going to sequentially go through, and it's going to replace candidate with instances of that particular population. In this case, it's the set of entities that are in that input buffer. Okay? So we set that. So we set my ranking rule here is first in, first out. My dynamic selection rule is smallest value first. Okay, so let's look at that. So when we run here, and we'll do the same thing. We're going to step. There's 1, 2. Still can't see them all, so let me zoom back in, way in. And what we see here is the ranking is exactly the same as what we saw before, right? The ranking is by the order in which they arrived from the arrival table. Okay? But when I select one, when I do the allocation, it reached in and said, hey, 6 has the smallest total processing time. I don't care what its rank is in the queue. Go in and find me the one that is. And so that's why you have to use the candidate. Because what the candidate keyword basically says is, hey, look at all those guys, 1, 2, 3, 4, 5, 6. Give me the smallest one. Okay, now, again, this is fundamentally different than using the static rule, because what the static rule says is, give me the first guy in the queue. So when you place them in the queue, they get placed in an order, and the static rule says, okay, give me the first one in the queue. That's why you don't have to use candidate, because it says, give me the first one. When we use a dynamic one, then we have to use candidate because we have to give it information about what's, that it's looking at all the candidates that are there. And so what we have are 2 different types of rules. We have a static one. The queue order is based on some static rules, and the first entity is done. So in Simio, those are called static ranking rules. And so we saw those. You can basically have smallest value first, largest value first, and so on. Dynamic rules, entities are selected from all the waiting entities. Okay, when an allocation is made. So here we had the, you can have the order, which is determined by the ranking rule, but the allocation is determined by the dynamic dispatching rule. Okay? Yeah?
Is there any advantage to doing it either way? And like, in what scenarios would it be beneficial to do it dynamically?
Yeah, I'm going to talk about that in just 2 seconds, but the short version in this instance, you would never do dynamic here because it's computationally expensive, right? Because every time you're recomputing everything. And for this one, there's nothing to recompute. Nothing changes. So, I get in the queue, and my total processing time is 12. Doesn't matter who gets in the queue around me. My total processing time never changes.
It's going to change depending who is going.
You want to use dynamic rules when something's going to change. Yeah, when something's going to change. And so if you look at the dynamic dispatching rules, so I'm going to go back to model here. To see these, you have to look in the help. I couldn't get all these in a slide. So if you look up this dynamic, let's just see if dynamic comes up. Dynamic selection rules. Here they all are. So you see a whole bunch of them. You see the one that we use, shortest, what do we do? Shortest, smallest value first or something like that? Yeah, smallest priority value. But there are a whole bunch of them, like slack time, shortest processing time. Critical ratios in there, right. And so a lot of these dispatching rules have implementation details, right? So we used a really simple one. Smallest value or largest value, just specify the values. But like things like critical ratio, which is, total time remaining divided by total time available, right? So how do you get total time remaining? Well, the total time remaining comes from the sequence, right? If you use setup, somewhere there's a setup, least setup time. Well, Simio has to know how to compute the setup time. So if I have a set of entities that are waiting in the queue, and I say, hey, I want to use least setup, you have to tell Simio, okay, well, here's how you compute the setup for the corresponding one. So again, there are a lot of these which we will see in detail here a little bit later on. The other thing about dynamic selection rules is we're looking at a very simple case where I had a queue that's waiting to go to one node. But the general case, I have a queue that's waiting to go to a set of nodes. So I have different selection. I have a selection of which one am I going to do with E1, E2, E3, and which node am I going to send it to, N1, N2, N3. And so this dynamic selection rule can be used to make those more complex decisions. Okay, so again, in summary, the ranking rule orders the queue. Dynamic selection rule selects the next entity. And if you leave the dynamic selection rule to be none, which is its default, just grab the first one. And then I think I talked about the queue. So static rules are really simple. First in, first out, default. Last in, first out, I forgot about it. Last in, first out is one. Smallest value first, largest value first. Of course, these smallest or largest, you have to say of what? Smallest or largest value of what? And so it's computed one time for each entity. So when the entity gets to the queue, you look at the value, and then you do a sort and put it in its location in the queue, one time. Dynamic selection rules, and we just looked at the help for details, it's recomputed for every entity on every allocation. So when an entity gets to a queue, it's just put according to its ranking rule, but when you're reallocating capacity, you compute everything, you compute the value for every entity. And then when that entity finishes in our server case, and you reallocate, you compute for everything again. Right, so the idea here is that it's computationally expensive. Okay, it's computationally expensive because for every entity on every allocation, you go through the computation. And so back to your case where you have 1 billion entities, you're going to do 1 billion calculations on every allocation. And so when you would use one versus the other, if the numbers don't change, there's no point in using a dynamic selection rule. If they do change, then you can't use the static rule, right? So it's kind of dictated for you about whether the values change or the values don't change. Some situations where I'm selecting between multiple nodes, as we'll see, we want to use dynamic even though the numbers don't change for a little bit different of a rule, but we'll see that probably not next week, but the next week. Okay, dispatching rules. Okay, so if we go back to our model, I don't want to use trace anymore. We stop the model. Go back in and see if I can reset everything back to where I was. Let's just reset this guy. There we are, I haven't changed anything. And we go to planning. And again, in this model, I'm only really interested in a couple of things. I'm interested in the make span, and I'm interested in the number of late jobs. These are the only two things we really track in this one. So we have a 61.8. Let me write this down. I won't remember it. 61.8. This is first come, first serve. What did we say? 4 late jobs. Go to my target detail. 1, 2, 3, 4 late jobs. 4. So this is make span, number late. And we go change the dispatching rules. So we're going to just do a couple simple ones here. So let's just go grab all of these guys. Let's do it by updating the custom object. So let's go to source 1 and let's change this one to smallest value first. We'll do total P time in just a second. Let's do date. So if I do smallest value first by order due date, I'm doing a rule called EDD, earliest due date. Okay, so I do earliest due date. And if I want to do the same thing in S2 and S3, I can go and change those like I was just about to do, or I can just right-click here and say update custom object from this. So when I update the custom object defaults, you can see that these automatically got updated because I changed the defaults on the custom object. And so every one of the instances that doesn't have the properties changed will update. Okay, and so then I go back and do my same planning. So I create my plan. Now we have 2 late jobs. And we have 58.6. So we have 58.6, 2 late jobs. This is EDD. And then the last one we'll look at is SPT, which I guess I should have done because I'd already had it set up to do that, but I didn't think about that. So just go back in and change this guy to, what is it, orders, total, P time. And then update its, update server from this, go to planning, replan, 53.8. And number of late jobs, 1. So SPT, asterisk, because it's not really SPT, but it's sort of SPT. I don't remember what it was, 53 point something, and 1. So yes, what we want to do is in the general scheduling sense is we're going to look at, a very rudimentary type, is to say, let's look at some different dispatching rules. And as we will see, when we start doing this, we're going to look at the Gantt chart and say, what do I want to happen here? What's causing me problems? And then we'll go in and make some adjustments. Yeah?
So why just sit right before you updated the objects based on the modifications on one of the objects, right?
Right.
So this only updated the object instances or the object reference as well?
It updates all of the instances where you haven't changed it. So because the other two, so I updated S1, right, and I changed the ranking rule, and S2, I had not changed it. It was still at its default.
Right.
So since the default changed, and this one was at its default, it updated it. Had I changed this one and it wasn't at its default, it wouldn't have updated that one. Yeah.
Is there a way to do like Smith's heuristic, like doing 2 different ranking rules?
On the same server?
Yeah.
Yeah. So you can have, and we will see that. So you can have, there's a tiebreaker rule. You can have multiple rules. You can say, apply this one, and if it's a tie, apply this one, and if it's a tie, apply this one, until it finds one. Yeah. And that's actually pretty common. Okay. So let's see here. The last thing I'm going to do today is give a brief intro of task sequences. And what I'm going to talk about today in the rest of class is just concepts of task sequences, because in the video, we implement task sequences for this. So a task sequence is a set of tasks that includes 2 basic components: precedence between tasks and conditional execution. So if you look at my server object up there, and this works for what I call server-based objects, so server, combiner, separator, and anything subclass from those. Right? We've talked about specific time. So we would set the time random dot exponential dot something, or we would set it to a table reference where we either had a random value or we had a fixed value or something like that. But we were saying use this specific time. A task sequence is something different. A task sequence is I want to do multiple things. Okay? And so each one of the tasks, when you specify a task sequence, each specific task has a process type, has its own set of resource requirements, material requirements, state assignments, and add-on process triggers. So we see that here, and this is for each task. Okay? And when we talk about task precedence, so the two things that we're interested in, at least for now, are task precedence, what we mean by task precedence, and process type. Okay? So we have typical sequence, so I can just have precedence relationships and this one before this one before this one. I can have parallel, or which is no sequence, right? No precedence. So in this case, the ones I don't have these nodes labeled, but these two, this one has to happen first, and these two can happen in any order, and then this one happens. Right? So these two can happen in any order, or they can happen in parallel. Okay, so I'm not specifying any precedence requirements whatsoever. And we can have arbitrarily complex task sequences. Okay, so this one, you're looking at this one and saying, okay, all of these tasks happen, at the server combiner, whatever you have connected. So task precedence defines this sequence, parallelism, and then combinations of the above. Process type is one of four things. So specific time is something that we've seen a lot of, right? So up here, if you look at this taxonomy, if you look at a server, we had these two categories. We had specific time and task sequence, and we've always seen specific time before. But in task sequence, when you look at each individual task, it can also have a specific time. We can have a changeover logic, which we'll see a little bit later on. We can have a process name, so we can execute a process. We can have a submodel, where we create a token and send it to the submodel. And so each one of the tasks can have its own defined process type. So task sequences add significant flexibility. Okay, so in our simple flow line model, I might have my first station has, a 3-stage sequence. My next one has this complex task sequence, and my third one has this, 4-stage, 2 sequential and 1 parallel task structure. Okay? And then, as I said, each task has specific processing type. So I might go in here and say, this is a specific time. This I execute a process. This one I do a submodel, all embedded within the same task sequence. Okay, so tremendous flexibility it adds, and then each one has its own resource requirements. So I can go to a server and I can have secondary resources and so on, and each individual task has its own set of secondary resources. We haven't done materials. We're going to do that next week, but each one has its own set of material requirements, state assignments, and add-on processes. So we can define the critical thing that we have to do here first is to define this task structure. Okay, so when you look at the set of tasks and you say, okay, well, how do I describe this precedence and parallelism? Okay, and there are 3 basic ways to do that. Immediate successors, 1. Immediate predecessors, so that's what we see right here. So here are the immediate successors. So just pick any task, and what this tells me is the immediate successors to that task. Immediate predecessors to that task. So if you're familiar with graphs, if you've done any kind of graph analysis, graph theory, anything, this makes perfect sense to you. Okay, it's just a graph. Okay, and once I know the precedence, I know how to do it. If you haven't had any graphs, this might or might not make sense to you. This is an interesting concept in Simio, is that some people find the graph notation easier, and other people find this third method, which is task numbering, easier. I find task numbering completely ununderstandable to me. I cannot understand it. I can usually work my way to it in the end, but it makes no sense to me. Okay, but a lot of people it does make perfect sense to, because they don't think in graph theory. They don't think in graph way. So there's the 3 ways, they all work equally well. Okay? One slight advantage of using sequence numbers is it's a single value, and so you have a single value associated with each node. Whereas with predecessors and successors, you have a list. I have a list of immediate predecessors or a list of immediate successors. And so if I'm doing any kind of automated processing, I have to do list processing. Where if I use sequence numbers, I just have a single token that I have to deal with. Okay, but still, I don't understand these guys. Okay, Okay, so if you were to come to me and say, I need help doing this task sequence, I can help you with predecessors and successors, but sequence numbers, I don't understand how they work. And here's the stuff from the help about what this means. You have the root sequence number, you then have suffixes, and you can have an arbitrary number of suffixes. There's a set of these 3 rules. Again, if it makes sense to you, more power to you. Feel free to use them. And we'll use them some. So if you have easy sequences like linear sequence, it's really simple to do sequence numbers. Or if you have just simple parallelism, it's really easy. It's when you get the complex graphs where it's complicated. I think I brought one here. Yeah, so here's one from the Semio Advanced Training. So in the advanced training, you give them this is a workshop where you say, okay, here's the situation. I think we basically gave them a graph view and say, now create the sequence numbers from that. Yeah, I couldn't do it, but here it is. Okay, so you can see the root number 10 and 10 and 20 and 30 and the suffix 1, the suffix 2, and so on. Okay? Well, as I said, a sequence number is one thing, right? So if I look at this graph, right here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 nodes, and each node is defined by one number. So this node's definition is 40.2.2. This one's 40.2.1. This one's 30.2. Where if I use the graph notation, for our example here, it's not a single thing. So if I look at 10, node 10, well, its definition is 2589. Right? So I have multiple things. So I have a list of things that define it. So for each node, I have a list of things that define it. Okay, so if you have to do any processing, you have to be able to process, the list of things. From a definition standpoint, and Semio interpreting it and executing it properly makes no difference. And that's my example. Okay, so we're going to see task sequences in video module 4. We do this one. So you take the model that I just built in class, or the one that I just built by hand. Using the template. And then we implement a simple task sequence. 3 sequential tasks, setup, process, cleanup. Okay, and so what happens in the video module, in video module 1, I implement the task sequence using the repeat group editor. So you just put the tasks in manually. In number 2, the video module 2, we look at secondary resources where I have an operator that does the setup, and I have an operator that does the cleanup, but the operator's not needed for the process. So that notion of secondary resources, so that's video module 2. Video module 3, we move everything out of repeat groups and into tables to facilitate this data-generated approach. Okay, and so this is a really simple task sequence here, but all of the stuff in that video is perfectly applicable to arbitrarily complex task sequences. That's what makes task sequences really useful. Is you can have simple things, you can have complex things, but they basically work in the same general way. And finally, I will end on this note of trace and symbits. We've seen trace. I've talked about trace. Don't forget about symbits. As I say here, symbits and trace are your friends. You need to use trace and symbits. In particular, if you come to ask me, we are going to start building more complex models. The 2 most common answers that I have when students ask me questions: my model isn't working as I expect. Will you help? My first question to you is going to be, have you looked at it in trace? And if so, what did you find? My second question, if I really don't understand Semio feature X, like task sequences or sequence-dependent setups or whatever, will you explain it? I'm going to say, have you searched symbits? When you say no, I'm going to say, well, go do that and then come back and see me. And I'm perfectly happy to discuss with you. But part of this process when you do complex modeling is learning how to do the modeling. If you don't know what's going on, learn how to do it. That's what we're trying to make sure that you can do. Okay, and so trace is always helpful. Symbits can be helpful often depending on what feature you're looking for. Okay, so don't forget about those 2 things as you start building more and more complex models. All right, any last questions for today? Yeah?
I was going to see if you could upload this onto Canvas.
Oh, the slides? Did I forget to do it again?
Just because I just uploaded the first 2.
Yeah, I updated it. I will do that as soon as I get back to my office. All right, see you guys next time.